Hey guys, today I've got a video for you on another branch of numerical analysis. We're going to be looking at numerical integration using the trapezium rule. So as the name suggests, the trapezium rule allows us to approximate the area under a curve using trapezia. And the more trapezia there are, then the more accurate the approximation is. So let's start by deriving the formula. So the trapezium rule allows us to approximate the definite integral of f of x between two bounds a and b. So we have our bounds a and b. In this case, a is equal to 0, but it doesn't have to be. And this is approximately equal to the sum of the areas of each trapezium. Let's call them a1, a2, and so on. We have 6 trapezia. And so our definite integral is approximately the sum of the 6 trapezia. So let's think about how we can work out the area of each trapezium. So imagine rotating each trapezium 90 degrees. Then the area of the trapezium is given by the height over 2, so h over 2, multiplied by the sum of the parallel sides. So the height is the same for each trapezium. It's b minus a over the number of trapezia. So h equals b minus a over n. In this case, n is 6. And the lengths of the parallel sides are given by the value of the function. So let's label this length here y0. Then we have y1, y2, y3, y4, y5, and y6. Then the area of the first trapezium would be a half times the height, h over 2, multiplied by the sum of the parallel sides, y0 plus y1. The second one would be h over 2 times the y1 plus y2, and then would continue. So now we have the area of each trapezium. Let's take the sum of the areas. So if we factorize out the h minus 2 from each area, then we get the sum of the lengths. So y0 plus 2 lots of y1 plus 2 lots of y2. And we have 2 lots of each length all the way up to y5, and then we have 1 y6. So this is our approximation for the trapezium rule when n is 6. Let's see if we can now generalize this formula for any n. What we get is h over 2 multiplied by the first length, y0, plus 1 of the last length, so that would be yn, plus 2 lots of everything in between, from y1, y2, all the way up to yn minus 1. So having quickly gone through where the formula comes from, let's now apply it to an example. So here is our question, and I've written the trapezium rule, which we've just derived, at the top of the page. And we've been told to approximate the integral of sec x from 0 to pi by 3 using 4 trapezia. I want to start off by saying that we could find the exact value of this integral using analytical methods, but remember the trapezium rule is part of numerical analysis, and so we're merely trying to approximate the value of this integral, and in this case we're using 4 trapezia. So let's begin by finding the value of h. So remember we defined h to be b minus a over n, where n is the number of trapezia, so n is 4, and b and a, they're the limits of our integral. So b is the upper limit, a is the lower limit, and so h is equal to pi by 3 minus 0 over 4, so pi by 3 over 4 is pi by 12. So we've got our value for h, And so now all we need to do is work out the values of y for each trapezium. And they're given by the function y equals sec x, where x is the lower limit of our integral plus the multiples of h, all the way up to the upper limit. So we're going to be working out the values of y for when x is 0, when x is 0 plus pi by 12, 0 plus 2 pi by 12, 0 plus 3 pi by 12, all the way up to pi by 3. So let's represent this in a table. So we have x and y, and the values of x are 0, 0 plus h, so 0 plus pi by 12, 0 plus 2 pi by 12, which is pi by 6, 0 plus 3 pi by 12, that's pi by 4, and all the way up to pi by 4 add pi by 12 is pi by 3. So now we're trying to find out the corresponding values of y. So let's just finish off this table. So the value of y at x equals 0 is sec 0, which is 1 over cosine 0, which is just 1. Sec pi by 12 is 1.035 to 3 decimal places. And remember, because it's numerical analysis, we're not trying to find the exact values of our function. A sensibly rounded number will do. So let's round them all to 3 decimal places. So sec pi by 6 is 1.155, and sec pi by 4 is 1.414, and sec pi by 3 is 2. So we've got our values of y, we've got our value for h, so now we can just plug it into the formula and see what we get. So this value of y, that's y0, this is y1, y2, y3, and y4. And so the definite integral from 0 to pi by 3 of sec x dx is approximately equal to h over 2, so pi by 12 divided by 2 is pi by 24, multiplied by y0 plus yn, and remember n is 4, so y0 plus y4 is 1 plus 2, plus 2 lots of everything in between. So we have 1.035 plus 1.155 plus 1.414. And the answer comes out as 1.336 to 3 decimal places. To finish off, let's consider whether our approximation is an overestimate or an underestimate of this integral. So here we have the graph of y equals sec x, and when we draw the trapezia, then what we notice is that a portion of the area of each trapezium lies above the curve. And so this implies that the approximation we got for the integral was in fact an overestimate, because we're including area that isn't actually below the curve. And this happens to be the case for any function that is convex in the interval. Whereas for functions that are concave in the interval, there will be area between each trapezium and the curve that isn't accounted for, which means that the approximation will always be an underestimate for functions that are concave in the interval. Hey guys, thanks for sticking around. If you want to learn about more methods from numerical analysis, then check out the videos on the screen, and I'll see you in a bit.